Hello and welcome to Mathematics with Simon. Today we're going to look at the important subject of proof in A-level mathematics. So what is proof? Proof allows us to demonstrate that a mathematical statement is definitely true. This is something that's unique and special to mathematics. So in mathematics we can know that things are true, whereas in science or in everyday life things aren't quite so simple. I mean, in science, we can get rules which we are pretty sure are true, or which we haven't yet proved false. But in mathematics, what's special about maths is, and what's special about logic, is we can know that things are true. There are various different types of proof. We're going to go through them in this video. So we're going to look at deductive, or what's also called direct proof, proof by cases, and proof by contradiction. So a deductive proof starts from known facts, things that we already know to be true. It then uses logic to get to the conclusion. For example, what we're going to look at is to prove that an even number times an even number is even. So let's look at this. So the first thing I like to do is just to try some examples. So just multiply together some even numbers. So 2 times 4 is 8, 4 times 8 is 32, 6 times 8 is 48. In each case, we've got an even number. This just gives us a feel for the theorem. And also, if we did get a product that wasn't even, we'd actually know that the theorem was false. That's what we called a counterexample. And it's always good to know that you're not trying to prove a false theorem, because that can waste your time. It would be unlikely that examiners would set you the challenge of proving a theorem that was false. But if you're doing maths research later in life, or also more generally when you're exploring things in work, sometimes you might be trying to prove things but not realise it's actually untrue. So doing a few examples is actually quite helpful. It just gives you a feel for it, and it lets you know whether there's a counterexample. If there's a counterexample, then the theorem actually was false. So let's look at a proof. Now we've tried 3 examples. So imagine that A and B are both even. So then we can write A equals 2 times M, because if it's an even number, then it's 2 times another number. B is 2 times N. This means that A times B is 2M times 2N, which is 4 times Mn, which you can also rewrite as 2 times 2Mn. So in other words, we've written A times B as 2 times another number, so A times B is even. We've proved that A times B is even. But also this proof actually suggests a new idea and a stronger version of the proof, because actually if A is even and B is any number, odd or even, then A times B is still even. So for instance, if we write A as 2n, then A times B is 2 times N times B. So it's 2 times N times B, which is a number. So therefore, A times B is even again. So now we're going to actually just explore an untrue theorem. So we've looked at an even times an even, and we've looked at an even times another number, which could be odd or even. But what if we're multiplying together 2 odd numbers? Well, let's pretend that that's going to be even. So let's just imagine we were given that untrue theorem. Well, we would try our examples. So we basically say, like, well, 3 times 5 is 15. Well, hang on, that's odd. 7 times 9 is 63. Well, that's odd. So actually, these are not even. So that theorem was untrue, and these are counterexamples to the untrue theorem. And perhaps our instincts then may lead us to the idea that an odd number times an odd number is always odd. And we're actually going to prove this by contradiction. So when we prove by contradiction, we imagine the theorem is false, and then that gets us to something that's totally untrue, so we realise the theorem must have been true. So let's try to pretend the theorem is false. So let's say we have A and B odd and A times B is even. Well, in that case, 2 would be a prime factor of A times B. If A times B is even, then 2 is a prime factor. And P is a prime factor of A times B if and only if it's a prime factor of either A or B. So if it was a prime factor of either A or B, then either A or B would be even, contradicting our hypothesis, because our hypothesis is that they were both odd. So by assuming there was a counterexample, we've actually managed to produce a contradiction because we've deduced that one of those initial numbers should have been even, but in fact we knew they were both odd. So that means the theorem actually must be true, and that an odd number times an odd number is an odd number. So what you do in proof by contradiction is you assume the theorem is false, and then you derive something which is patently untrue, which makes you then realise the theorem was true. So here are some other theorems about odd and even numbers. I mean, these may come naturally to you. An even number plus an even number is always even. An even number plus an odd number is always odd. An odd number plus an even number is odd. That's very similar to the second one, it's just reversed. An odd number plus an odd number is even. We're going to prove one as an example. We're going to prove that an odd number plus an even number is odd. So let's say that A is odd and B is even. So we say that A is 2 times m plus 1, where m is a whole number, and b is 2 times n. Then A plus B is 2m plus 1 plus 2n, which is 2 times m plus n plus 1, which is odd. So we've shown that a general odd number plus an even number is always odd. And we can prove these other 3 theorems in the same way, similar ways. So here's something a little different, proof by exhaustion. This is called proof by exhaustion. And in proof by exhaustion, we take various different cases. So let's say that x is a whole number. We're going to show that x squared plus x plus 1 is odd for all whole numbers x. There's basically 2 cases. X can be even or x can be odd. So let's start with x as even. If x is even, then x squared is an even times an even, which we've shown is an even. Then we're adding it to itself, which is an even plus an even, which is even. And then we're adding on an odd, and then an even plus an odd is an odd. So we've shown that in the case of x being even, x squared plus x plus 1 is odd. Now let's imagine that x is odd. In this case, you've got x squared is an odd times an odd, which is odd, plus another odd, and as we've seen, an odd plus an odd is an even. And then we're adding on 1 at the end, which is an odd number, so an even plus an odd is an odd number. So in both cases, whether x is even or x is odd, we've shown that this sum is an odd number, and those are all the cases. There's no other possibility like x is either even or odd. So when you do proof by exhaustion, you have to exhaust all the possible cases. But there are only 2 cases. X can be either even or odd. Okay, now proof by contradiction. We're going to exercise our proof by contradiction muscles here to show that. And this is a big deal, which was a big result for the Greeks, because the Greeks were very big on geometry. We're going to show that the square root of 2 is not a rational number. It can't be expressed as a fraction of 2 whole numbers. And to show this, we're going to assume the opposite, and then we're going to get to a contradiction. So we're going to assume that root 2 can be expressed as a over b, where a and b are both whole numbers. Then we're going to express a over b in its lowest terms. Now let's check in our minds that we know how we can always do this, because the way we do this is we express both a and b in terms of their prime factors, and then we cancel out any common factors, and we cancel down to a fraction in its lowest terms. So a over b is in its lowest terms. Now, root 2 is a over b, so we square both sides. This tells us that 2 is a squared over b squared. Or, multiplying both sides by b squared, we get 2b squared equals a squared. Now, the fact that a squared equals 2b squared means that a squared is even. And from our previous work, what we can see is that a cannot be odd, because if a was odd, then a squared would be odd. So a must be even. And we can say that a is 2 times c, since a is even. C is a whole number. So now we substitute that a equals 2 times c, so 2b squared equals 4c squared. Divide both sides by 2, b squared equals 2c squared. So now, since b squared is even, we know that b must also be even. But we actually assumed that a over b was in its lowest terms, and we found out that a and b are both even. So actually now we've contradicted our hypothesis, which shows that root 2 cannot be expressed as a fraction, because by assuming that it can, we've got to an absurd result. We're going to use the same method to show, this is a really powerful method, to show there are infinitely many prime numbers. So a prime number is a number that's only divisible by 1 and itself. Let's assume there are finitely many prime numbers, p1, p2, p3 up to pn. Okay, we multiply them all together, p1 times p2 times p3 times times pn. And then we add 1. So, now what is this number? It could be a prime number. If it's a prime number, it's a new prime number because it's bigger than all the others. So it's out of our list, which contradicts our hypothesis. If it's not a prime number, it has prime factors, but it can't be any of the p1, p2, p3 to pn, because in each case, if we divide by p1, p2, p3 to pn, we're always going to get remainder 1. So none of those go in exactly. So the prime factors must be outside of this group. And so therefore that contradicts our hypothesis, because our assumption was p1 to pn was all of the prime numbers. So since we've managed to contradict our hypothesis and come to an absurd result, there must be an infinite number of prime numbers, which is actually a very important outcome. As a special bonus, we're actually going to prove there's an infinite number of counting numbers, just an infinite number of numbers. Because let's assume there was a biggest one, so there's a finite number, so there's a biggest one, and let's call it n. Well, in that case, n plus 1 is also a counting number, right? You can always add on 1, and it's larger. So that contradicts the hypothesis, so there must be an infinite number of counting numbers. Okay, so we've looked at various kinds of proof. We've looked at direct proof, where you start from things you know to be true and then just use straight logic. We've looked at proof by exhaustion, where we go through all the different cases and in each case prove it to be true. And we've looked at proof by contradiction, where we assume the theorem to be false and then we get to a result that we know is untrue. Therefore, the theorem must have been true. I really hope you like this video. If you do, please hit the like button. You're very welcome to subscribe and hit the notification bell. We'd love to hear your ideas. I hope you enjoy your mathematics, and we look forward to speaking again soon.